Hi, my name is Yuki Ikuta. I'm with Design Group Los Angeles, and I am thrilled today to be talking with Mark Koebrick. He's our Senior Process Specialist out of our Northern California offices. Hey, how is it going, Mark?
Hey, it's going really well. How are you doing, Yuki?
I'm doing great. I am really appreciative of your time. I wanted to see if we can take a couple of minutes today and talk about what sterile boundaries are in the biopharmaceutical world. Do you have some time?
Absolutely. It's a fun topic.
Wonderful. Let's begin with the definition of what sterile is.
Okay, so sterile is really in a biofarm environment is that it's defined as a probability of a viable bioburden or microorganism survivor of less than one chance in 1 million, basically a 6 log reduction of the environment. Um, and this is often confused with sanitary, and a lot of people will say, well, it's sanitary and sterile are the same thing. It's significantly different. Sanitization and disinfection is really defined as eliminating many uh, of the pathogenic microorganisms, but not all of them, and it certainly doesn't eliminate bacterial spores on inanimate objects. So those are particularly difficult to eliminate. Uh, so the common target is usually a 6 log reduction. Uh, and then you determine that by first establishing what the D value is of the prevalent organism within your maybe an environment, whether it's prevalent within the facility you're working or such.
I understand. And so there's not one way to sterilize, right? So talk us through a couple of different methods for sterilization.
So there are several. One you'll hear about is ethylene oxide. And ethylene oxide is a gas, and it's beneficial when you have heat sensitive, components. Let's just say that you have something that you can't heat it up to a sterilization temp. So the ethylene oxide works well for those. One of the downside of ethylene oxide is that it's heavily regulated by the EPA and OSHA. It's some severe flammable hazards and severe health risk. So that's one. Another is irradiation. Irradiation is a very common sterilant used for single use. So you'll get a lot of single use components, and they'll be pre sterilized through gamma or beta or electron beam type irradiation. And they work. It actually works very well. The downside would be that you have to pre-order your equipment enough in advance so that they have time to do the irradiation. But it's very effective. Dry heat sterilization. Dry heat sterilization is just basically taking the temperature in a dry heat upwards of 180 degrees Celsius and holding it there for 2 hours. Uh, and that differs from depyrogenation, which is also a dry heat, but the depyrogenation is usually reserved more for your stainless or glassware. Let's just say you're a biopharm company that's filling vials with vaccine. You want to make certain that you don't have any pyrogens left. And pyrogens, of course, left over from bacterium, from the lipopolysaccharide membrane of gram-negative bacterium in particular. And to eliminate that, you have to heat it at an extremely high temperature for a very long time. So the target is typically between 200 and 300 degrees Celsius for a minimum of 2 hours in order to remove those pyrogens, and that's with a dry heat. And part of the reason you use the dry heat also is that if you're filling vials, maybe you have a 2 ml vial, you certainly don't want to fill it with something that's a liquid, like saturated steam. Of course, then that brings us into saturated steam, and saturated steam is a very effective sterilant as well, and it's been commonly used in the biopharm industry for a number of years. And the difference between saturated steam and dry steam or dry heat is basically 3% moisture. So
Mm,
the perfect saturated steam is 97% dry, and that 3% moisture is what makes the difference, and it's a very common sterilant used. Um,
So let's talk a little bit, I guess, about the biology of SIP.
Okay, so So I mentioned that the biology or the steam is 97% dry. So when it comes to microorganisms, they have the the membrane, of course, and in order to kill that microbe, you really want to get to the nucleus and the DNA and denature the nucleotides. So to do that, you need to break through that cell wall, and that 3% moisture within saturated steam is really the magical component that breaks through that membrane, cell membrane. And then when it does, then it lets the heat get in and denature the nucleotides, and that's really where the effective kill is. Um, so yeah, and of course, there's a lot that goes into designing an SIP system that's effective. Make certain that it takes a little finesse to make sure that you're designed properly.
Oh, absolutely. It's certainly not something that people can do straight out of college, and it takes years to develop great design considerations.
Well, one of the things with steam and basic physics, people think you just hook steam up to a vessel or a pipe line that it's going to necessarily sterilize it. Unfortunately, because it's a gas, in order to make that gas move in the direction that you want it to, you have to create openings. So basically show it the door out. So you put it in one end of one system, you want to show it the doorway out in the other system, out at the end of the system. And you do that with creating pressure drops. The pressure drops can be in the form of steam traps, which is it collects the condensate and naturally dispenses it. And it can also be, let's just say, if you're taking a vessel that you're trying to sterilize, you might put the steam in somewhere near the top of the vessel, but there's always air inherent within steam, and there's always air that's going to be in that vessel before you start. So you need to evacuate that steam from the top, or that air gap from the top of the vessel, so that that saturated steam touches all surfaces to have an effective membrane inactivation and kill of the bacterium. And to do that, you would create a pressure scheme, so you have a pressure drop, and you do that with by putting more pressure in the vessel and then letting some of it back out, and then creating that pressure drop through typically a back pressure controlled proportional valve. And then, of course, with any of this, once you sterilize, you want to make sure it stays sterile. So then you create, some method of maintaining that sterile boundary. And typically, you would choose a 0.2 micron filter, and you have those in place, and you'd steam through them. And the 0.2 micron is chosen because unless you're talking about mycoplasm, the smallest known bacterium is 0.2 or 0.25. So that would prevent any ingress from coming back in. And then when you're done sterilizing, you usually put a slight positive pressure. Anytime you heat something up, just like if you remember your parents canning at home, they would pull all the lids shut on top of the cans. It draws a vacuum. So you want to make sure that you create a slight positive pressure, either in an inert atmosphere, maybe using nitrogen, or maybe compressed air, but you send it through one of those pre-sterilized 0.2 micron filters, so that you have this pressure scheme so that's slightly positive to the outside surroundings.
Absolutely. And, I think we've been talking and kind of targeting this discussion a little bit more around traditional stainless steel tanks. I wonder if you could talk a little bit about the nuances with sterilization and single-use equipment.
So single-use systems are they're actually really great. They're typically sterilized either using irradiation that we talked about earlier, or they're autoclaved. That's something we hadn't talked about. Autoclave is basically a saturated steam and bringing up the temp, and then you're looking for a 6 log reduction. And so you can usually, when you get to the single-use systems, they come within pre-sterilized, or you can sterilize them within your own autoclave. And the benefit of the single use is that they're extremely simple to use. They've taken a lot of the complexity out of it. We just talked about how you design a steam in place system. They've done that for you, and they've made it almost foolproof when you connect it to where you prevent contamination from ingress of microbials, just in the function of how they connect. And they have 2 films that separate the sterile from the non-sterile, and you remove them, then you've created a sterile pathway. there are actually a lot of benefits to them. And one of the complexities of single use is a lot of people still have traditional stainless steel systems. You need to interconnect between them. So you need to be a little savvy in how you come up with the different connectors and hoses and fittings so that you can create a hybrid system. So you could connect an existing stainless steel system to to a single-use system. But there's certainly the components are out there, and you just need to talk to the right process people to help you with that.
Well, I'm sure as people have, they will give you a call. So I appreciate your time and effort and energy into talking with us today about this topic. And I will talk to you soon. Thank you, Mark.
Well, thank you. It's been a pleasure.